Welcome to Brain Vision.
So we will be using the equation for Compton effect over here. So lambda dash, that's the wavelength of the scattered photon minus wavelength of the original photon, is equal to h over mc, where m is the electron rest mass, h is Planck constant, c is speed of light, times 1 minus cos phi, where phi is the scattering angle. And we will be using one more equation. So energy of a photon is equal to h times frequency, and that is equal to hc over lambda, where all the variables have the common meaning, have the general meaning. So frequency is f, c is speed of light, lambda is wavelength. Now this from the first equation, so this is actually delta lambda, the change in wavelength. And for part A, we need to find delta lambda, so we can directly use this equation, and we already know h over mc. So h over mc is actually Compton wavelength. So we can substitute that value along with phi, and phi is given to be 35 degree. So, or you can choose to substitute h, m, and c separately and solve this equation, and make sure h is in units of joules seconds. M is the mass, so that has to be in kgs, and c is in meter per second. So that way you get delta lambda to be equal to 4.388 times 10 to the power minus 13 meter, and this is equal to 4.388 times 10 to the power minus 4 nanometer. Oops, I forgot to write the value of Compton wavelength. So this is equal to 2.426 times 10 to the power minus 12 meter. Okay, so now we have delta lambda. So in the second part, we need to find wavelength of the scattered photon. So from this part, just this part, we can say that lambda dash is equal to lambda plus delta lambda, and lambda is given to be 0.0425 nanometer. So we can plug both the values of lambda and delta lambda. We have both of them in nanometers, so no worries in any conversion. And we get lambda dash in nanometer as well. That's equal to 0.0429 nanometer. Then in the second part, we have to find the loss in energy. So we will use this equation and use it to substitute over here. So we know that change in energy is E2 minus E1. So here we will just use this equation. Don't worry about the above equation. So let's call this equation 1 and equation 2. Yeah, sorry, equation 2 and this equation 1. So we are using equation 2 here. Now we will use this equation and for each of these energies. So we have hc over lambda 2 minus hc over lambda 1, that is equal to hc times 1 over lambda 2 minus 1 over lambda 1, and lambda 2 here is wavelength of the scattered photon, so that is lambda dash, and lambda 1 is wavelength of the incident photon or the original photon, so that is equal to lambda. So now again we can substitute the value, solve for delta E, and that way we get this delta E to be negative 4.358 times 10 to the power minus 17 joules. And make sure while solving this equation, you convert these units of lambda and lambda dash into meters, and also h should be in units of joules. If you want your energy to be in joules, and if you want your energy in units of electron volt, use h in units of electron volt. So here I have used H in units of joules, but if you use H in units of electron volt, your answer should be negative 272 electron volts. So from here, because of this negative sign, we can say that there is a loss in energy and the photon loses an energy of 272 electron volt. So in part D, so by applying the principle of conservation of energy, we can say that the energy lost by the photon is the energy gained by the electron. So the electron gains an energy of 272 electron volt.